Hello, this is Greg Partika, and I would like to share with you an approach that we've developed at OpenGeo Solutions that helps bridge the gap between seismic processing and interpretation. With this approach, we set out with a couple of main goals in mind. One is to generate a set of attribute and inversion products that ensures no important details are missed. And secondly, to present the information in a way that preempts the time-consuming preparations that so often plague multi-attribute investigations. What we do is generate a comprehensive library of pre-rendered images that covers the dimensions of the attribute space. We capture these at the sample rate of the data, which means that the image library can easily contain millions of images. It's not that we expect you to want to examine all the images, but what we want to make easier is the task of spotting interesting features and then to be able to track the anomalies through any number of dimensions to determine which dimensions are going to be most telling with respect to localization and identification. Of course, we still deliver the digital data in SIGWI form, but the pre-rendered images can be easily viewed right away using a web browser, so there is no new software to learn, and with the content all pre-rendered, there are no bottlenecks with data access or with data preparation. Here on the screen is an example of what this looks like. There is a control panel here in the center. It lets you navigate through the various data options and dimensions. On the left, we have browser windows for inline at the top and cross-line displays here at the bottom. The cross sections can be viewed either on structure or flattened relative to a guide horizon. On the right, there is a plan view display. We typically capture plan views using a step size that is equal to the sample rate of the data. To minimize cross-cutting through stratigraphy, we tend to capture these plan views relative to a guide horizon, or sometimes we use a straddle approach, which allows you to step percentage-wise between a series of horizons. To start out with, we are displaying the input data. Red here represents negative amplitude, and blue represents positive amplitude. No dataset is ever perfect, so it is important to be able to compare the raw versus denoise data at any time for any attribute. So here we have the raw data at a time of 210 milliseconds, but by toggling on or off the denoise, we can compare the noise suppression and what it was able to do. So here's noise suppression on and off, and notice that as I turn that on and off, it also changes not only the plan view display, but also the cross-section display to see the effect. Since the noise suppression looks to be pretty good, I'm going to leave that on. And typically, when I first look at a new area or a new zone of interest, I tend to look at the spectral decomposition. So I'll turn that on. And when you select that, you get a grayscale. White is high amplitude, black is low. And that activates the frequency bar here at the top. And now, with that turned on, I can move up and down in frequency. For example, here we are at 15 hertz. I can move up to 20, 25, 30, and so on to see what difference that makes to the imaging. When I'm trying to investigate a particular feature, what I tend to do is turn to the time RGB view of spectral decomposition. When I turn that on, I no longer get just a grayscale display. We are now blending three separate spectral decomposition displays as red, green, and blue. We're still centered at 35 hertz energy, but now in red we're including an image that comes from slightly above this level which we're at, which is 210, and in blue slightly below the level which we're investigating. What that allows you to do is identify whether the feature you're interested in, for example, this body right here, and this breakthrough that seems to be happening right there, it's showing up as more reddish in nature. And so that's telling us that the imaging of that feature is coming predominantly from a shallower interval being imaged by the red. So if I move to a shallower level, we'll see that we see less of that red. If we continue moving shallower, we'll see that it's actually becomes a bluish hue, which is telling us that now we've moved too shallow and that there's better imaging to be had of that feature if we move down in time. So I'm just going to do that, move down to 200. That seems to be a good balance between the red, green, and the blue. And now that we've localized in time, we can switch to localizing in frequency. I'm going to turn on the frequency RGB view. And now we're no longer blending a shallower time and a deeper time. We're now blending 3 different frequencies, in this case centered at 35 Hertz. In red, we're seeing information come in from lower frequencies, and in blue, they are coming from higher frequencies. And just as we were able to localize in time, we can now use this approach to localize in frequency. This feature that we're interested in is exhibiting a reddish hue, which means that there's more energy coming in from the lower frequencies. So now we can just move to a lower frequency until we lose that reddish hue. Now if we go too low, it's going to appear more bluish, as it does right here at 20 Hertz. So I'm going to move back up to 25 and maybe even as high as 30 Hertz. So this kind of approach lets you localize in both time and frequency. So there are a variety of other attributes that can be helpful. And remember that we've created these images, and there's a library of them, and the goal is not to guide you through a particular path through the attributes. The goal here is to let you look at this information and decide what might be important to look at next. So let's just turn to discontinuity attributes, spectral discontinuity, using the full bandwidth of usable signal. And now that we've localized that feature in time, we can see that it also shows up quite nicely as a discontinuity, both the break through it and the edge of it here. Sometimes it's quite effective to overlay the discontinuity over top of other attributes. Let's go back to the time RGB view and now overlay the spectral discontinuity. Since the discontinuity is captured with a grayscale, it can sometimes darken the image, and so it quite often is helpful to brighten the image afterwards. So I'm going to brighten that image, and now we really have the best of both worlds. We have the spectral discontinuity, which provides context, and we have the morphology and heterogeneity information that comes from the RGB view of spectral decomposition. Let's turn the brightening back off and turn the discontinuity off. Another family of attributes that can be very helpful is the curvature set. And the curvature attributes provide important information regarding flexuring. And when you turn any one of these curvature attributes on, for example, Kmax shows both the highs and the lows associated with the flexuring. As soon as you select any one of these curvature attributes, it activates the curvature exponent scroll bar. The curvature exponent is important because it allows you to control the spatial scale of the flexuring that you're imaging. If you select a curvature exponent that is quite high, for example, +1, it's going to be targeting very small scale features. And as you slowly decrease the curvature exponent, 0.8, 0.6, 0.4, 0.2, through 0 and into the negative range, you're looking at larger and larger scale features. And in our case, the type of feature we're looking at, it's actually much better imaged at the negative alpha range, maybe even as low as -0.6. Let's turn on the discontinuity overlay for context. And so once again, you get a combination of attributes where the whole is greater than the sum of the parts. We've got the discontinuity providing context, and within that, the flexure information is telling you that this feature we're looking at is a relative low with respect to the background. Other attributes that are available include bluing, which is band-limited reflectivity. Here, negative amplitudes are red, positive amplitudes are blue. So in red we're seeing the transitions into softer bodies, and in blue the positive amplitudes are showing transitions into relatively harder bodies. And likewise there is colored inversion, which shows band limited impedance. Once again, reds are negative and blues are positive. Now whether you're looking at colored inversion or bluing, that changes the view not only in the plan view display but also in the cross sections. And it also activates the choice of the high cut shape, because remember, when you're looking at bluing and color inversion, there is an aspect of spectral color, but also there's an aspect of shaping, that is the filter shape, where the high end slope of the filter controls the interplay between side lobes and resolution. So for example, now that we're looking at bluing, you can select a 2-octave high end slope of an RSB filter, where the 2-octave very gentle slope means that you're minimizing side lobe interference, but at the expense of some resolution. You can have a slope that's not quite as great, for example a 25 Hertz slope, that will allow some amount of side lobes, or you can even go to a 10 Hertz slope here, where you're getting quite a bit more side lobe energy, but with that you're also hopefully getting a bit more resolution and detection. Another attribute that can be quite effective is spectral inversion layering. That's where we are using the full bandwidth of available signal to predict the architecture of soft versus harder bodies. This often looks quite a bit like the CI, the colored inversion, but the CI tends to not be quite as well resolved typically. Remember, the CI, we can control the high end slope. If you compare that to the spectral inversion, you can always now look at the values in plan view. For example, this feature we were looking at, the bluish nature of it means that it's a relative hard with respect to the background. You can turn on culture overlay information to orient where you are. There are also crosshairs here that help you go back and forth between what you're seeing in cross-section views and the plan view. The horizontal lines here and the cross-sections indicate the time slice or plan view that we're looking at. The crosshairs in the plan view indicate where we are in the inlines and the cross lines. And of course you can move up and down as far as inlines and cross lines to move around and investigate different features. So hopefully this gave you a flavor of what the Navigator technology can do, and it showed you one path through the various dimensions that are available. Thank you for your time and for your interest in seeing what this is all about.